Let's talk about the dynamical system in general. In general, a dynamical system can be represented in the following form. We have n equations, and the left-hand sides of the equations are the derivatives of x1, x2, and xn. So we have n differential equations of the first order. This can be also transformed to the differential equation of nth order. The right-hand sides are the expressions f1, f2, and fn, or the functions of x1, x2, and xn. And here is the order of the system, and t usually represents time. The over dots denote differentiation with respect to t, so xi dot is dxi by dt. Please note, all fi's here don't depend on t, so this system is autonomous. If all fi's are linear, then we can say that the system is linear. If there is at least one nonlinear fi, then the system is nonlinear. For example, we studied this system, and what we see is the linear system because the expressions of the right-hand sides are linear expressions. So we have the following representation. f1 of x1 and x2 is x2, and f2 of x1 and x2 is just minus k over m x1 minus b over m x2. And we have two equations, so this system is second order linear autonomous dynamical system. Let's start from the first order linear systems. We have the first order, so n equals 1, and the system can be written in this form or in this form, dx by dt equals ax. At the position x of 0 equals x0, the solution is the following. This is the solution of our system because if we differentiate it, then we will reach the right-hand side of initial equation. C here is a constant which depends on initial conditions x0. Let's study the behavior of this first order linear dynamical system. We can have the parameter a positive or negative. When a is positive, then the x, or the solution of the system, will grow exponentially. If a is negative, then x, or solution of the system, will decay exponentially. So if a is positive, then our x is diverging and system is unstable. It means we can start from any initial value of x. Our x will be increasing as t is increasing. For our negative a, we see that x is converging and system is stable because we can start from any initial value of x. Our x anyway will be approaching 0 as t increasing. So please note that the sign of the parameter a determines whether the system is stable or not. Now let's look at the second order linear systems. Since we have the second order, our n equals 2, and the system can be written in this form or using the notation dx by dt, or in a shorter form, x dot equals a capital X, and x dot here is a column vector with the components x1 dot and x2 dot. A is a square matrix 2 by 2, and x is a column vector with the components x1 and x2. And as you remember, in the last time with the first order linear dynamical system, we determined whether that system is stable or not without solving the system itself. The same question we have here. Can we determine whether the system is stable without solving the differential equation itself?